Yeah, thanks very much for the invitation. It's been a lot of fun seeing all the things going on here. It's a very interesting place. So, what I'm interested in general is how our perceptual system processes the natural world. And this is sort of in reaction to, I guess when you're approaching complex problems, you have a tendency to simplify. And we have to simplify things to make them tractable. And we look at natural scenes or listen to natural sounds. We idealize the environment. We say, well, let's do line drawings and images, or maybe for sounds, we'll do a very special class of sounds. But the problem I'm interested in is how do we solve the natural problem where the signals you're processing have all their complexity. And when you want to represent those signals, how do the things we know and use generalize to these complex sounds? And another interest I have is how does the brain do this? Because we can propose algorithms that does this, but it'd be nice to know if there's some underlying principle that can guide us for what good ways, bad ways, principled ways, or unprincipled ways. And one of the ways we can approach this is to look at what the brain is and construct hypotheses for what the brain is doing to try and understand why it does what it does. So today's talk is going to be about sound. And the general problem that I'm interested in is sound seems like a particularly hard problem if you explain it to someone. And if you assume a sound didn't exist, you'd say, well, you have two inputs and they vary in time. And from this you can get all kinds of information. What I'm saying, where I am in the room, the acoustics of the room, and all this stuff. And how is it that we look at all of these different waveforms and say that, oh, they're all the same? Or no, in fact, they're all different. What is the structure that we're pulling out? So there's a lot of ways of processing these kinds of signals, and a simple way is just to take a bank of filters. You can look for the energy at a particular frequency, for example. That's what a Fourier transform would do. So you take your input signal and you put it through a bunch of filters, and what we'll tell you is the time-varying energy at each frequency. And that might be useful. It's maybe a very crude approximation of what our own ear does. But really we're interested in something more. And also, well, why should we do this? Is frequency the only way we can analyze signals? Another way you can approach it, which is very common, is to take a more discrete approach where what you do is you start with a signal and you break it up into chunks. And once you do that, each chunk you can sort of process independently. And you can transform that into whatever set of features you want. They could be frequencies, if you're doing Fourier transform. If you're doing wavelets, then you can look at time and frequency. And basically anything in this box you can transform down here, and then you have a set of features that hopefully will give you information about the kinds of structure that you're interested in. So that's all engineering. What if we looked at what the auditory system is doing? Well, if you look at the auditory system, this is the inner ear, the eardrum, and the cochlea. And this looks really complicated. It's not a box. How do we understand what this is doing? Is it even possible to have an abstract description of it? So most of the talk will be about how do we develop an abstract description, a holistic description of how we approach coding. And the basic problem is you have the pressure waveforms here, and you have to send a signal down, say, the auditory nerve. We can look at each part and describe what it's doing, how it transforms energy and things like that, but can we say what it should be doing from underlying principles? So to approach this problem, first you have to understand how it transforms sound, and the way to do that is to be a neurophysiologist and record the activities of all these auditory nerve fibers. And traditionally this is done in cats, and what you do is you stick a very fine glass electrode or some other type of electrode into the auditory nerve, and you can record the electrical activity in response to incoming waveforms. And what you can do then is try and characterize each nerve in terms of how it responds to sound. And you can ask the question, for example, what's the best filter that I could, what's the best filter for approximating the way that this particular nerve responds to sound? And it's possible to answer that question, and physiologists answered that question in the late 60s. And what they could measure was essentially the filters of the auditory nerve. Now, of course, this is just an approximation because the cochlea is very a nonlinear system. So even the notion of describing it in terms of filters is questionable, but it actually allows you to explain a lot of what it does. And when you look at the filters, they look like this. These are actually the time domain filters, and the way to interpret this is they have a particular resonance frequency. So there's the time scale. So these are sort of high frequencies. That one up there is low frequency. And the other important thing is how much time they integrate over. So you all probably know about having a long window FFT versus a short window FFT. That's basically changing your integration window. And the auditory system does the same thing. You know, the longer you integrate your signal, the better idea you have of where the frequency is, for example. And what the auditory system does is kind of something intermediate. At high frequencies, it integrates over a short period of time. And as the frequencies get longer, it sort of stretches out and integrates over a longer period of time. And it's very specific about the way it does it. And actually, it's so specific that you can model these functions. And physiologists have done this too. And the way you can model them is basically with the resonance frequency. This is the cosine part here with a phase to shift it back and forth, and an envelope, which you can describe as a gamma function. And the gamma just means it has this particular shape. It has a rapid rise and a slower decay. And the amazing thing is that these gamma tone functions can describe almost every auditory nerve filter you can measure. And so when you fit them, they fit quite well by adjusting the frequencies, the amplitudes, and the rise and fall in that. And so you can actually look at the residual error. How well did it fit? Well, there's not too much residual error here. So it describes that kind of structure pretty well. And what you find is that the frequencies are sort of distributed along the cochlea a fairly specific way. And this envelope part, the gamma tone, or the gamma part of it, also follows a very characteristic pattern. So the only problem with this is that we still don't know why the auditory system is doing it this particular way. It could have done it different ways, right? It could have integrated over a longer period of time. Maybe it would have been better to, I don't know, if what your animal really had to do is localize sound. And if you think of an animal in a noisy environment where it has to listen to rustles of the leaves and things like that, is this the best way to solve that problem? And we don't really know the answer to that question. But what it says is there might be other ways to represent sound, and merely describing it doesn't tell us anything more fundamental. So the approach I want to take here is a theoretical approach. And what I want to do is make a distinction between modeling and theory. And so what we've done so far is model it. We've described this function in terms of a small set of parameters, 6 or 7 or so. And so when we do modeling or make theoretical predictions, we're trying to explain the data, right? But we're going from different directions. If we do modeling, we start from the data and try to find a simple description that explains it. But theories are different. Theories are driven by sort of underlying principles, where you say this is what the system is trying to do in general, and then you try and make predictions from that fundamental principle. So theory allows us to answer different kinds of questions. For example, why should we use this particular shape? Or why should we encode sound in terms of spikes? Or how is the sound encoded as an ensemble, right? When we just fit a single function, we don't really know how all of these things work together to encode complex sounds. And that's the kind of question I want to be able to answer. Another thing you can ask, which is a good thing to ask whenever you deal with biology, is should you expect there to be a theory, right? When we think of physics, well, of course, the laws of gravity and Newton's laws and things like that, those seem pretty fundamental, and they explain a lot of things in the real world. But biology, That's evolution. And why would we expect that evolution would be anything more than just whatever works? And it's a very complex system, and it's always adapting. Is there anything more you can say about it, right? It could be that the simplest description of the cochlea is the cochlea itself, right? It just is the way it is because that's the way it evolved to be. But let me give you a different argument. And this makes use of actually eyes, so we'll go over to the visual modality. Now, eyes are very interesting because if you had proposed vision before vision existed, it would have seemed fantastically hard, right? There's some electromagnetic energy out in space, and what you're proposing to do is to be able to remotely sense all kinds of things about the environment. You know, how far away something is, and you can recognize the identity of other creatures. And if you were a jellyfish living in this kind of environment, it would just seem impossible. How are you going to perform this computation? But eyes did evolve, and what's interesting about them is if you look at the whole range of possible eyes, there aren't very many. And so Michael Land and his colleagues went out and characterized the types of eyes you see in the animal kingdom. And there's only a half dozen or so. And they're very constrained in terms of their design, quote unquote. And the reason for that, we can look at it now and say, well, of course, it has to obey optics, right? Because the underlying problem any animal using an image is trying to solve is it has to focus light somehow, right, if you want to use that information. And that's the problem you're solving when you're doing the remote sensing, right? You're basically, your lens is like a computer that's taking all of these light and focusing them on one thing so that you can form an image and remotely sense what is over there. So the shape that these can be and the density that the media can take on is very constrained by underlying principles. And you could describe eyes as solving the problem of how to focus light. And if you knew that, you could actually go and predict the shapes that all of these things could have. The space that it occupies is very small. So we can observe that, and it seems kind of impossible that eyes could even evolve in the first place, right? Because they're so complex. But actually, you can look at evolution and identify all of these intermediate steps, and many of them still exist today. If all you start off with are sensors, then you have an ability to detect whether you're facing away from light or toward it, right? And that's useful. If you want to know up from down, for example, if you're a sea creature, that's functional. And if your system is changing shape and it happens to kind of form a cavity, well, now you've got a little bit better detector, right? Because now you can create a shadow, and now you have this aperture looking out at the world. Well, if it bends over a little bit more, then you have a pinhole camera, and now you're starting to get a very crude image. And if there happens to be another membrane over it, well, then, you know, and so on. And what they showed is that it takes about 500,000 years, just assuming simple 1% differences from generation to generation, to evolve an eye. And the important thing is that what it's evolving toward is constrained by this underlying space. There's an underlying problem, you can think of it, that the eye is solving. And there's only one way to solve it, or there's only a small number of ways to solve it because of the principles of optics. And when it gets there, the solution stabilizes. That's the important concept. So you can't focus the light any better, right? So once you've done that, there's, in a sense, not much more you can do. You can evolve other kinds of structures to kind of give you an aperture. You can sort of do some additional focusing and so on, but you're very constrained in terms of the total space. So could that be true for neural processes? Well, it's true for the eye, it seems to be, and what had to co-evolve along with the eye are this stuff here, all these sensors, right? So all of that stuff, an eye doesn't do you any good unless you can process the information. So along with this evolution of optics, there had to be an evolution of how that information was processed. And maybe it's the case that that information processing is similarly constrained by these underlying principles. If what you have to do is code the information or detect movement or other things that animals need to do to survive, perhaps there's only so many ways you can do that. And there's an optimal way to do that. And once you've done it, the system stabilizes around that solution. So if all that is true, it really simplifies our life, right? Because instead of looking at biology as this hugely complex system that is impossible to make sense of, you can expect that there actually are underlying principles that you can identify and explain all of these little parameters. So that's theoretical models. We want to explain data from principles, but we're trying explicitly to make an abstract model. So what is the principle? Well, one idea that goes back to the 50s is the idea of efficient coding or redundancy reduction. It was first proposed by Horace Barlow and earlier by Fred Atneve. And the idea is that since you have limited resources, one thing that makes sense is that it has to get the information. And if you think of all the ways that you could code information, what would serve the animal best if it has some kind of efficient code that makes best use of whatever resources it has. Take the auditory nerve. There's only so many auditory nerves, and you're constrained in terms of how many of them you can have. So it would make sense if, over evolutionary time, the apparatus has evolved to sort of push as much information as possible down this information channel. And once it does that, it sort of stabilizes. And if that confers an evolutionary advantage to the animal, then that will continue to evolve. Now, this isn't the whole story, I should emphasize. There are some caveats. First of all, we can't treat information generically. We can only consider behaviorally relevant information, things that are important for the animal's survival, but we can kind of define that in a fairly generic way. And the other thing is, redundancy isn't all bad. So the notion of efficient coding itself is only a first approximation. There are other factors that come into play once you consider the limitations of the system, but for now we'll just concentrate on efficient coding. So let's go back and look at our different kinds of representations. We could answer the question here and just say, okay, well, let's take a sample of sounds and say, what's the best way to transform it in a way that's the most efficient? But there's a lot of problems with this because it doesn't match biology. For one thing, it's linear, and we know that biology is highly nonlinear. And if you are nonlinear, you can be much better about the kinds of codes you can get. The other thing is the code is only optimal for a given block and not for the whole signal. And we expect that evolution is operating on all the sounds that it hears. So whatever sound you're listening to, your system is adapted towards processing that whole sound, not some arbitrary block that you specify. The other thing is it doesn't offer any explanation of phase locking or spikes, which are fundamental properties of the auditory system. So we would like that to somehow be involved in this explanation. So we can do something better. You might think, well, what if we just use a filter bank? A filter bank doesn't depend on these blocks. And maybe you can think of that as phase locking. It doesn't depend on the alignment of the block. But the problem with that is that you really haven't done yourself any good. You've taken one continuous signal at the top and converted it into n continuous signals, right? So where's the efficiency in that? You've actually made your life a lot worse. And so what we really want is to find a representation that is efficient and also time relative in the sense that it doesn't really depend on the absolute time position. Now there's one way you can approach this that we worked with, which is atomic basis decomposition. And it's a very simple idea. And the idea is that you can look at a sound and describe it in terms of features. And these features can be anything you want. In the end, what we're going to do is adapt the features so we can learn the best set of features. But the big difference between block coding, where you're chopping it up and transforming it, or more like a convolutional code where you're taking a bank of filters, is that you're placing these features exactly where they occur in the sound. So mathematically, it's a very simple model. You just add up all of these features at their precise time positions, weighted by the degree of presence of that feature in the signal. And so here these features are those gamma tone functions. We just chose them by hand, and you can see that they can be different lengths of time. They can be different in frequency, and we kind of arbitrarily center them on some point, and that's the position of that feature. So this has the advantage that it exactly aligns with the structure down to the sample level. And it also has the advantage that we can reconstruct the signal exactly to an arbitrary precision. So that's good for our efficiency. And so here's an example of that. I should mention one more point, which is that if you're really concerned about biology, you might be getting nervous at this point because you're thinking, well, wait a minute, these are analog and spikes are binary, but that's all true. But really the point here is to try and find the most efficient representation and see what we can predict from that. We can further constrain the model to make it more biologically plausible, but at this point what we want to be driven by is the idea of these fundamental principles, that if we could find the most efficient code and adapt that to our natural sound environment, then we'd be able to predict properties of the auditory system. So we have to tolerate a certain level of abstraction in order to do that. So here's the way these codes look. This is a segment of speech, and if you take these functions, what you can do is sort of fit these kernels and find the sparsest set of features that describe your signal. And what you can show is that the reconstruction can be basically as small as you want. So you can get arbitrary fidelity for a wide range of different features. You can see that these features, if they're oscillatory, can exactly line up with the oscillations you see in the signal, which in this case is a vowel from speech. And it even can capture the different harmonics components. So here, this is higher frequency, so the red here corresponds to the spike there. I should now point. I'll do that with the mouse here. So here's the feature, which has this center frequency and exactly that position in time. This one up here is higher in frequency, and it has much smaller amplitudes, so the spike is small. And these other ones here repeat. So that, notice, lines up exactly with the voicing harmonics. And it occurs again right over here. All right? So you can reuse these features. And from a small set of spikes, you can reconstruct very accurately. And we can contrast this to something you're more familiar with, which is a spectrogram. And in a spectrogram, what you do is you have a window, and then you take the Fourier transform of the things in that window. And spectrograms have this characteristic smearing pattern, right? Because they're essentially redundant representations. There's nothing saying that this frame has to be representing different information from the next frame over. It's sort of very continuous. And for that reason, you have this time-frequency trade-off, where when you blur the signal with the window, you're losing your time information. So one of the advantages of the spike representation is that the time remains precise. So these features tell you down to the sample where that acoustic structure is in the speech. Oh, you have a laser pointer, great. So if you compare these, this represents the signal exactly. This doesn't. It represents the time varying frequency information. It's losing all the phase. I'm still pointing with my finger. So actually this represents more structure, but it's much more sparse, right? You're representing it with a smaller set of signals. And I haven't told you how we compute these. We use an algorithm called matching pursuit, which is just an iterative way of figuring out where all of these features are. And there's a bunch of different algorithms you can use. That's actually an active area of research. But for our purposes, we have a representation that's very compact. And so now what we can do is go off and do some science. But first let me show you kind of how this works. So here's the word can. This is a oscillogram. And this is represented with just 36 spikes, 36 of these features. And if I play this, I'll play the whole sentence that this is a part of. So it's only 5 dB signal to noise. It's a very compact, sparse representation, but it still sounds speech-like. And it's able to capture these harmonics you can see here because those are exactly aligned with the features themselves. If we set the threshold lower so that we get a higher fidelity sound, we add more spikes. So now we've got 3 times as many, 93. And you can see the fidelity is getting better. Our residual error is going down. And if I play it now, it'll be perfectly understandable, I hope, modulo the room acoustics.
Fill that canteen with fresh spring water.
So it's noisy, obviously, but we're not really representing it with much information at all. And so that we can control this. And when you go up to 20 dB, now we have a lot more spikes, almost 400. And our residual error is now down close to the actual noise level.
Fill that canteen with fresh spring water.
And so the speech is understandable. And you can keep going. So one of the nice properties of this is you can represent things more or less to arbitrary fidelity. And so you can get a very flat residual error. And then what happens is that you get all these little features that essentially represent the background noise. And the nice properties of this is now that we have a time relative representation that can sort of lock on to the structure in the signal. So if we look at this is actually the sound R, but it's sort of falling off, so you're getting individual glottal pulses right at the end. And you can see that these spikes are aligning with those pulses. And so the sparseness of the representation is maintained, and even some of the relative structure is maintained from glottal pulse to glottal pulse. You can pull out very specific kinds of speech structure. So this is the word Vietnamese, and that little blip right there on the amplitude waveform is the T in Vietnamese. And the way the speaker says it is sort of very quickly, Vietnamese. So there's just a little blip. And it shows up in the Fourier representation as this smear of energy, right, because you're smoothing over it. But in the spectrum, it's just 4 spikes, because that's all it takes to represent that sound. And what we can do is sort of pick it out by hand, and it sort of perfectly leaves the voicing behind, the vowel part of the speech. So this is a very efficient representation. We can quantify the efficiency precisely by essentially quantizing the amplitudes and times of this representation. And we can compare it, we can make an apples-to-apples comparison to things like Fourier and wavelet transforms, because all they are in terms of this representation is a set of features which happen to be sines and cosines of an exact length which spans the block, and where the spike times are restricted to occur periodically, right? And so we can take a representation like that and fit it just as well using our algorithms, and then we can quantize it and just measure the coding efficiency. So when we did that, what we see is that the signal-to-noise ratio at a given rate, so the way to read this is the spike rate, right, in terms of kilobits per second. So it's like your MP3 player. MP3 is, of course, way out here because you're recording a very high-fidelity signal. Here, the relevant range is where the structure is. So, I'm sorry, high fidelity is up this way. This is the rate. So for a given rate, for a given fidelity, like say 15 dB signal to noise, which is perfectly recognizable speech, as you heard, we heard 10 and 20. For the same fidelity, the spike representation is 3 times more efficient. So it's a huge difference. And later on, we'll adapt the kernels. You can do it even better. The important thing to understand about this graph is your win comes down here, which is where the structure is. As you increase the fidelity, as you demand higher and higher fidelity, what happens is that you start to fit noise in the signal. And a fundamental property of codes is that they're adapted for the structure you say. And if you ask to fit random structure, the code can't fit that very efficiently. So it can only fit it up to about between 30 and 40 dB, because after that point, you're just fitting noise, right? And there's no structure in the noise, so the model has no advantage over any other code. And so they kind of converge. And actually, it's even worse because our code, when it's adapted, is adapted for particular kinds of sounds, not noise. Okay, so now what we have is a theory. We have a coding theory which tells us how to code sounds, and we have a model. And so once we have this, what we can do is go and make some predictions. And so the main points here, we can code signals accurately and efficiently. And they're much more efficient than block codes. So we might expect that when we adapt this kind of model to the sounds that biological organisms have evolved to process, if the theory is right, we should be able to predict some of the structures of biological organisms. So now what I look at is coding natural sounds. So to give you a picture of what's going on, this is the natural sound environment, and we don't really have a good way to define that, but we know what kinds of things animals have to do. They localize things in the environment, they have to recognize the calls of other animals, they have to be alerted to the presence of things. So whatever their natural sound environment is, evolution evolved a way to deal with that. And the way it has these particular auditory nerve filter shapes and the way they're organized in a population. So that's the data we have to work at. Now what we're going to try to do with this theory is take the same sound environment, but then predict these shapes and predict their organization in the population. And we don't know a priori what that's going to be because our input to this is the natural sound environment. And so the important point is that it's not modeling. We're not giving it the shapes of the auditory nerve. We only compare to that after we've made our prediction. We don't fit the data. So the big question here is, well, what is this natural sound environment? How do we define that? This actually took a little bit of work. The first time we tried this, we couldn't really get a match. And initially we had divided the world in terms of vocalizations and environmental sounds. And our thinking was that vocalizations are important for animal communication. So if we just take a large database of animal vocalizations, mammalian vocalizations, and combine that with environmental sounds, the kinds of things you might hear walking around in the natural environment, that should predict the auditory code, but it doesn't. So we had to make two more distinctions. And what turned out to work very well was to divide environmental sounds into transient environmental sounds, the kind of a cracking type sound, and ambient environmental sounds, which is sort of a rustling type sound. And when we weighted these equally, it worked much better. So let me give you a sense of those sounds. These are animal vocalizations. And this is from a Cornell database. So they're not really harmonic at all, right? There's screeches and cries and all kinds of things, but they're still very different in terms of acoustic structure than the environmental sounds. Here's a squirrel. So there's lots of chirping, short bursts and things like that. It's a very wide range of sounds, and we just put the whole CD into the algorithm. And then what we did is we went out and actually recorded as many environmental sounds as we could. And so we walked around on leaves, we did it in snow, we cracked branches and things like this. And we just tried to get a large variety of sounds to try and approximate the natural acoustic environment. So cracking branches are another example of transient sounds. And you notice how the sound structure over time is very sparse. And that's not true for ambient sounds. It's like when you have rustling leaves, this might be a bush, like an animal moves through the bush, it just makes a shaking type sound, right? Or if the wind is blowing it or something like that. So it's not sparse over time. Water is very similar. We have more of a continuous type sound. And the thing about both the animal, or both the ambient and transient sounds, is they're not harmonic, right? And the interesting question for us was that a Fourier representation seems like a natural choice for sounds that have harmonic structure. But it's not obviously the best choice for these non-harmonic sounds, like leaves. Can you does it make sense to take the Fourier transform of a cracking twig and analyze that? Well, it's not clear. So we recorded a lot of sounds. And then what we could do is say, okay, here's our natural sound database. Let's take this parameter here, which are our features, and just optimize them so that we can most efficiently code that acoustic environment. And I can give you a picture of what the learning is like. We start the kernel shapes out randomly, and we also adapt their length, and that's very important. So they can be as short as they need to be or as long as they need to be. And any change they make, they're making because they have a more compact representation of this acoustic ensemble. So this is what it looks like when they adapt. And what each of these plots are is one of those acoustic features. The gray bar is the time. It's a 1 millisecond bar. So you can see that we have kernels that get very long and are low frequency, and then the high frequency ones can be quite short, just a few milliseconds. The plot down here shows the two things we're interested in, which is the signal-to-noise ratio, or the fidelity that we're fitting the structure with, and the coding efficiency. So we're fitting better with a lower coding cost, or the entropy of the code. So it's working. And what you see is that they converge to a very regular shape. And it doesn't really matter where you start this from. Different random conditions lead to more or less the same patterns. And so we get a set that looks like this. And so now when we've done this, we've derived this set of features from just the natural sounds. So then we can go and compare that to the physiological data that the physiologists have measured. And that looks like this. So Laurel Carney put a whole database of these features on the web. And these are the auditory rev core filters that they measured from the auditory nerve of cat. And you can see they more or less look the same. You have sort of low frequency oscillations. Some have a lot of oscillations. Some have a very sharp onset. Others are more gradual. So there's a whole range of different things. And what we want to know is, how do ours compare to theirs? Well, what we can do is, for each of our kernels, we can find the closest one in this database of about 100. And so we say, okay, for this one, we can find a cat auditory rev core filter that matches fairly well. And then we can go ahead and do that for the whole, keep going. And they match remarkably well. Like, even these low frequencies, you might have expected that the envelope maybe is regular, but some of them have very few oscillations, and some of them have a lot. And the structures match up. Actually, they match up so well. You remember I showed you that residual error with the fitting those gamma tone functions. The residual error of these functions, which weren't fit to the data but derived from natural sound, actually give you a lower mean squared error than gamma tone functions actually fit to each individual auditory rev core filter. So they're capturing some structure that is useful for coding and sounds efficiently. It's dependent on the sound ensemble, and so what we can do is see how much of a dependence there are. Here's that population of rev core data, and what this plots is the bandwidth of a particular function versus its center frequency. So if it has very low bandwidth, let's see. So like when it goes up, they tend to have very sort of high bandwidth. They spread out, which means they're getting very short in time. When you get lower in frequency, the bandwidth goes down, which means they're relatively long in time. And they have this characteristic shape, and then they spread out.
Can you say just a couple more words about exactly what these rev core, what was measured in the cat?
So the way they do this is, it's a system identification method, and they play white noise to the animal. And when the auditory nerve is listening to this sound, you get a spike train out. And then for this, what you can do is average all of those spikes, and that will give you an estimate of the best filter that drove that spike. And they did it for different sound intensity levels, so from, I think, 40 dB all the way up to 90 dB. And there's slight changes as you change intensity, but I think we used like 80 dB or something like that. But basically what it is, it's a way to derive the filter that would best predict the output of that auditory nerve fighter. So if you took that filter, convolved it with that input signal, and just thresholded it, you couldn't do any better than what you estimated. So if we give it different kinds of sounds, for example, if we only gave it these environmental sounds combined together, we see that we don't predict this population. The filter shapes wind up being too short, and they're all consistently above what you see in the population. If we code animal vocalizations, they lengthen out, which means their bandwidth is getting very narrow, and so they're consistently below. But if we mix them together in this natural sound ensemble in roughly equal proportion, then they fall right on the data, and they even match the spread. So that's something we didn't expect at all, because when you look at a given frequency, there's a range of different bandwidths. So it integrates over a range of different temporal windows, and that seems to be matched in the auditory rev core data. When you run different simulations from random starts, it sort of matches that. So what this says is that natural sounds seem to be divided into this space where you have animal vocalizations at one end, transient environmental sounds often in other dimensions, and ambient in a third. And this is the acoustic space you're trying to represent. And we did a really crude search to try and best match the data. And it really didn't take much work. So in roughly equal proportion, they give you that match to the auditory rev core filter. So let me show you a quote. This is from a conference in 1950. And I don't know if any of you are Bayesians and know I.J. Good, but he's a relatively famous Bayesian. And it was a symposium on information theory, and all the luminaries were there, including Shannon, and Cherry was there, cocktail party problem, and Dennis Gabor. And and this was the time when people were in conferences, they published the question and they published the answer, which is great for posterity. We don't really do that anymore. And so he said, I cannot help wondering whether it is not largely a prejudice to analyze signals in terms of frequency. You have to think back in that time, nobody could really do Fourier transforms, and they were thinking about what kind of transforms would you do, and that was just one of the things you could do, so the mindset was very different. And the best person in the world to answer this question was none other than Dennis Gabor, who's responsible for the time-frequency distribution and the Gabor function, and he won a Nobel Prize in holography for inventing holography. And so he says, well, actually, no, there are two good reasons for choosing Fourier representations. The first is that you have this infinite or semi-infinite time axis, and then that's why you want to use a Fourier representation. And then problems are usually stationary. They're homogeneous in time. So just based on those two things, you can say that Fourier transforms are completely characterize that space. But he said once one or two of these conditions are dropped, then it might be worthwhile to consider other forms of the representation. And so for natural sounds, neither of those things are true, right? Things are transient. They're not stationary. And you're never dealing with an infinite time axis, right? You're trying to describe structure right there.
May I ask, what did Dennis Gabor mean about problems being homogeneous in time?
Basically that it doesn't matter where you sample, that they're homogeneous, that the statistics now aren't going to change tomorrow or an instant from now. They're not dependent on some context.
What sorts of problems was he thinking about that where the temporal layout is not interesting?
It's a good question. I don't know. Yeah, but when you think about it that way, it's hard to think of an example for which that's true, right? Yeah. Okay, so there's another thing I want to say, which is that we found this really nice fit to the population data for natural sounds. What was amazing is that the first time Evan ran this program, he ran it on the Timedomain speech database, and we got this answer. We got all of those functions you say the very first time you run the simulation, which if you've done simulations never happens. It's probably the only time in my life that it will ever happen. I was fortunate to witness it, but that was very curious. You think, okay, I'll show you the answer. So here it is, the same thing adapted for speech. Fits beautifully. Now, why is that? And it took us another year to come up with a set of natural sounds that had the same acoustic composition. But speech had it straight away. And so what's going on here? What it says is that natural sounds give us this nice shape, where the theory predicts what you get in a cat, and speech also predicts what you get in a cat. So you can ask the question, are cats adapted to speech? Maybe. That's why they're so responsive. But of course, there's another way to think about it, which is that really our auditory system is evolved in this acoustic space, which has a particular kind of structure. And the point of communication is to communicate information, right? So if you put a constraint on that, I want to convey as much information as possible. I have a limited bandwidth, certain kinds of acoustic features that I can use. What's the way that I could sort of push the most information through my limited channel? Well, it turns out speech falls right in that same place. And the acoustic structures that we use kind of match these three things. Vowels are similar to animal vocalizations. Our hard consonants are very like transient environmental sounds, and things like sibilants and fricatives are very much like these ambient sounds. And those, in roughly equal proportion, give you these auditory features. Okay, so in the last part of the talk, I want to sort of change gears. So what we've talked about so far is all this theoretical neuroscience and coding, and that's all great. But is it really getting where we want to go in terms of how do we understand the environment? How does our auditory system pull out all of the structure from sounds? And I think you would have to say no. You can describe it, but you still don't understand it. So how do we get there? And we can go back to this problem. Sure, we can describe every wave, and we can do it in a very compact way, but it doesn't tell us what this is, or it doesn't allow us to say whether this is different from that, or even part of the same class. How would you approach that problem? So this is a problem that we can also approach using statistical learning. And the idea is that at a more abstract level, we can learn representations that take a whole ensemble of patterns and try and find the underlying structure. And so all of these algorithms, statistical learning algorithms, are really about finding underlying structure. You have this low-dimensional space, which you can't see, right? But it's there because it's like when I talk, my voice is constrained by how I move my mouth and my vocal tract and things like that. And that's a much lower dimensional space than the waveforms that are going into your ear, right? So there's that underlying space, but it's not directly observable. So what we would like to be able to develop are algorithms that can kind of find the space automatically, because it's too difficult to introspect about it. And this goes back to the issue I brought up at the beginning of wanting to understand natural sounds. We can investigate acoustic structure, and this linguists have done this since the 50s, and analyze parts of speech and characterize them in terms of their frequency components and amplitude envelopes and the way the formants change and all of these different things. But we still don't know whether that kind of description generalizes to all sounds. Is it appropriate to use those kinds of features, for example, for describing consonants? And I think there's a fair argument to be made that we haven't really understood how to represent consonants, because that's the worst part of any speech recognizer, right? We can do vowels fairly well, And it's fairly easy to pull vowels out of noise, but when it comes to consonants, we're still pretty bad. So one of the things we wanted to analyze was impacts, and this is work by another student of mine, Sofia Kavako. And she was interested in metal bars. And metal bars are kind of interesting because a lot of work has been done in them. Physicists have modeled them. We can talk about resonance and other kinds of physical properties. But they also have natural variability. So if you take a bar, the same bar, and sort of hit it as regularly as you can with a hammer, you'll get a different sound out every time. And so this is what it sounds like. It's kind of a clank, right? It's harmonic, but it's not harmonic because it's got that clank in the beginning. And what is that? And if you listen to these, they're all different. If you look at the waveforms, you'll see how different. But yet they all sound the same. You know, they're similar. But they're not similar in terms of the waveform. They're similar in terms of some more abstract space that we can't get at. So how do we get at that space? So you can see the variability here. This is a spectrogram of the sounds. And if you just look at here, you can see how the harmonics vary. Here's A1, A2, A3, and whoops, that's doing something completely different. Even though, you know, we just let this thing fall, and it should be the same, but it's not. There's slight variations, and they lead to variations like this. If you look at B, it's the same thing. Here, it's even more variability. You know, these are not the same at all. And we recorded these sounds in an anechoic chamber, so there's nothing else going on. Right? It's not like there's some fan in the background that's affecting the. It's really the actual variation in the bar. Same thing for D. You know, here, all kinds of different things happen. What's going on there? And sometimes you even get total dropout of the harmonic. So here, harmonic, 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 nothing. Totally canceled out. So it disappears. So in order to call these things the same, what we have to understand is what that underlying space is. What are the perceptual dimensions that we're using, or that the bar, for example, varies in, that we're calling the same? And if we understood that, then all these bars would sound similar. If we approached it, I said a lot of people have worked on this, so there's been very detailed models of the physics of this. And they can generate a fairly realistic sounding bar, but what's very difficult to capture is the variability. So you run this model, it'll generate the exact same waveform every time. There's been other approaches. One approach to that, so computer graphics people are very interested in because they want to generate realistic sounds in computer games. And that's a non-trivial problem because it's hard to get that kind of variability. And so one approach is to have a robot sort of poke something in a controlled way, and then you get these waveforms and you try and fit the parameters to the different impacts. And so it's realistic, but still many things are hard to simulate. It's hard to get a realistic sounding clank sound, for example. A much more sophisticated way to do it was by Doug James. And what he can do is you put in a mesh grid model of your material, and he can actually simulate the vibration, the vibrational modes of this. And so you actually synthesize the whole sound wave. And this sounds great, very realistic. But of course, it's tremendously computationally expensive because here you're simulating the whole thing. And so you haven't gotten at these underlying perceptual dimensions. So we wanted to take a statistical learning approach, and our idea was to try and take the simplest approach possible. And so I'm not even going to use any of that fancy spike coding stuff. It's just sort of straight linear transforms and using independent component analysis to find compact representations. So the data we want to fit are, this is a spectrogram of the impact. And we have a whole bunch of these. Dozens for each type of bar, and we have different metals and even a wood bar. So a huge database, and the game basically is to, what's the most compact representation of the database that you can find? And so if you knew the underlying perceptual dimensions, or if you, not necessarily perceptual, but if you could figure out the features that characterize this whole database, then perhaps those would correspond to these perceptual dimensions. And you have some choices you can make. One is, do you want to represent the features in time or features in frequency? And if you represent them in frequency, what that means is that your model says, well, there's a set of harmonics. Those are your features. And then the way those harmonics change over time is scaled by the coefficients in your description. So that's basically a harmonic model. Okay? What we're trying to learn is the fundamental set of harmonics that we mix together to explain all of these different impacts. Conversely, you can think about, well, let's describe the amplitude variation. And so what that says is that things decay in different ways. And what we're going to do is we're going to describe all of the different decays for all of the different bars and try and define the most compact set of decays that describe the data set. Now this might seem like they'll give you the same answer because it's a linear transform and you're really just fitting a matrix, but statistically they wind up being very different and they give you very different answers. So initially when Sophia was doing that, I thought, obviously the frequency representation is the way to do it because it's a harmonic sound. And when you do that, you kind of get some interesting structure. Okay, so these are the frequency features. And what they tell you are that, well, here there's sort of a base harmonic for the bar. And there's another one that's very similar, but it is sort of slightly different, so it can account for different kinds of harmonics that you can see. But you also get these things, which are sort of single frequencies at different weights. And if you mix these together, what you can do is account for any kind of harmonic you see in a frame. And these are the actual coefficients, right? So you can see how the harmonics change. Sometimes you get ringing, so that's why these are large, because by the time you get over here, this feature, which is right there, turns on, right? And all the other ones are very close to zero. So the initial harmonics are present right there and right there, and so it kind of makes sense. But then one day, Sophia comes in and she goes, well, I really don't think this is the right way to represent it. And she shows me this other data, and she says, no, time is the best way to represent this. Really, all the structure is in the amplitude. And she showed me this. And so if you think of amplitude features, then all of a sudden you get these beautiful smooth features where it's possible to describe the whole database in terms of basically the attack, a short attack, a mid-range attack, and then ringing. And the way these work, now you're doing it this way. And what you're doing is saying at different harmonics you mix in different ones of these. And so you get the flip of what we got before. And what you can also do beyond that is you can learn a basis for describing these. So you can take these whole set of complex sounds and map them down to a very small space, basically describing these coefficients, and then another small basis which describes sort of features in the frequencies. And what's interesting is you get different amplitude features for different types of metal. So the aluminum bar, for example, has a very strong ringing component. It has sort of 2 mid-range components and 1 very sharp attack. Steel, on the other hand, looks very different. You've got 3 very sharp attacks and then sort of 3 different long decays. And what's remarkable about this is that this small description is enough to capture the natural variability you see. So what this is an amplitude profile of one of the partials, of the one that beats. And when you hit the bar different times, this is the aluminum bar, you get different kinds of beating, and that's the variability that you hear in this natural sound. So this is the natural variability. If we just take our low-dimensional representation, which is now just between 5 and 10 parameters, generate it randomly according to the statistical assumptions of the model, we get the same kind of variability. Right? So sometimes we get a lot of ringing, sometimes you get a sharp attack and then ringing, sometimes it's primarily the attack and no ringing, and all of these kind of match what you see there. And so what that suggests is that we've uncovered this low-dimensional space where you have sort of natural variability, but then if we synthesize from the model, we stay within that same space. And one thing we're really interested in doing is say, well, how good is this? Have we really uncovered perceptual dimensions? So what we want to do is synthesize these sounds and ask, can people tell the difference? Can they identify sort of variability introduced by the model that's not realistic? Well, if you've ever done synthesis, it's very difficult not to synthesize something without artifacts. And Sophia really wanted to have this in her thesis. And so she spent like a whole extra year trying to develop synthesis algorithms that were artifact-free. That part's complicated. I won't describe it here, but just to say that in this particular description, you're missing the phase information, so you have to be very careful about how you fill it in. But you can fill it in a way that doesn't introduce artifacts and preserves the structure of your low-dimensional representation. So once we have that, we can synthesize these sounds by basically varying the number of components that you use to do the synthesis. And so we can mix in different pairs. We can play the real sound that we recorded. We can play the real sound with the original coefficients, which is essentially the same as the real sound. We can play the new coefficients, which are the ones that we got by synthesizing from the small set of parameters of the new sounds. And we can play catch sounds too, which are just randomly generated according to random statistics and see if people detect it. And what we do is mix in varying numbers of these features. So this is the result. And what you see is it hardly takes any features at all to get to the level where they can't distinguish between the real and the synthesized sound. This is for aluminum. So here what it says is that with just 3 components, you're already up at like 90%, a 90% match between the real and synthesized. And you can do a little bit better, but actually past this point, none of these are statistically significant. Not any different from adding all of them in there. Steel is a little bit different. It's a more complex space, so it takes a little more to describe. And wood is a little bit unusual because that seems to take more to describe. And if you add information, for some reason it sort of introduces a particular kind of structure that people can identify. But once you get up to 10, then people can't tell the difference anymore. So you're going from a whole waveform down to 10 features and back, and people can't tell the difference.
Why is there a dip when you add features?
Well, yeah, this is intriguing. I'm not sure that we really understand it. When you listen to these, when you add this extra feature, it seems to it's paired up with this. They're not completely independent. So when you add this, you hear some little weird thing that doesn't sound quite right. And when you add another component, it seems to compensate for it. So it's something like that, but I can't really give you a...
Groups of features that
Yeah, they're not completely independent is the best way I can explain it. So of course this was all in the Fourier phase, and what we would love to do is apply these same kind of techniques to the spike code, but we're not there yet. So let me just close up by doing one thing with the spike code that Evan did that's kind of neat, and that's to do the synthesized sound. So we said that the spike code was sort of the most efficient code, and that it sort of represented the auditory system. So if you play the spike code backward, if you synthesize from random spike code, that should be the most natural sound. And so what do you think the most natural sound would sound like? Well, here's what it looks like. And what this is, it's just a bunch of little gamma tone functions mixed together at various amplitude. And we control the sparseness. And if we increase the rate, it sounds like this. Or decrease the rate, I think. So that's just straight out of the model. And here, the advantage of it, we don't have to do any fancy phase inference and things like that. It's just straight out of the model. But of course, our real stream still has more structure. Right? Now that kind of sounds nice, right? So we're not there yet. So let me sum up. In the first part, what I try to emphasize is the value of theoretical models and the idea that biological systems have evolved sort of information processing ideals, and they're constrained by these underlying principles of information processing. And we can predict codes quite well, and there's a whole other side of this in vision, where you can also predict a lot of codes. And where this is going, I would say, is to try and get beyond coding, to take these statistical models and try and figure out structure that is more abstract, sort of reduced representation that captures these lower dimensional underlying spaces. So let me end there and take questions. Thank you.